Tonight we journey into the hushed, crimson embrace of a world that has long captivated our collective gaze. We drift towards Mars, our closest planetary neighbor, a sphere steeped in ancient mystery and the enduring whispers of potential life. For generations, dreamers and scientists alike have pondered its silent expanses, imagining civilizations, or perhaps, simply the faint stirrings of microbial existence beneath its rust-colored plains. Our tireless quest for these elusive answers has propelled us across the vast cosmic ocean, sending forth a fleet of robotic explorers. These silent emissaries, rovers and orbiters, have diligently chronicled the very fabric of Mars, capturing its rugged, ethereal beauty in resolutions so sharp, so exquisitely detailed, they transcend mere imagery. They transport us, in a quiet, almost dreamlike fashion, to its distant shores, allowing us to perceive its awe-inspiring features, its venerable landmarks, with an intimacy that would have been utterly unimaginable to the stargazers of a mere century past. The planet, often referred to as the Red Planet, possesses a singular, striking hue, a deep, pervasive reddish-brown that seems to seep into the very core of our human imagination. It is a color born of time and elemental transformation, a visual testament to forces that have sculpted this alien landscape across billions of years. As we gaze upon these vistas, a quiet contemplation settles upon us, an unspoken question of what it might truly feel like to stand upon that ancient, ochre soil. What wonders, what desolate grandeur would unfold before our eyes? What profound secrets does this silent, rust-hued world still hold within its vast, unyielding embrace? So, before you get comfortable, take a moment to like the video and subscribe. Let me know in the comments where you are in the world and what time it is for you. When we consider Mars, particularly in the grand, sweeping context of our own familiar Earth, a fascinating, almost uncanny sense of kinship begins to emerge. For an alien world, cloaked in such a stark, reddish mantle, Mars is, surprisingly, not as profoundly foreign as one might initially conceive. There are echoes, subtle yet persistent, of our terrestrial home woven into the very rhythm of its cosmic existence. One of the most striking, and perhaps comforting, of these resemblances lies in the fundamental measurement of a day. The solar day, on Mars, known as a sol, unfurls itself in a duration that is only marginally, incrementally longer than the familiar 24-hour cycle we experience here on Earth. To be precise, a Martian day extends to 24 hours, 39 minutes, and 35 seconds. This slight elongation, a mere whisper of additional time, allows for a familiar, almost parallel cadence to daily existence, a subtle cosmic synchronicity that might, one day, provide a small comfort to future human inhabitants. However, when we turn our attention to the Martian year, the disparity becomes somewhat more pronounced. The annual journey of Mars around its parent star, the Sun, stretches considerably beyond our own 365-day terrestrial orbit. A full Martian year encompasses approximately 1.88 Earth years, or, when broken down into a more tangible measure, it equates to 1 year, 320 days, and approximately 80.2 hours. This extended orbital period, this longer, more languid celestial dance, is of course entirely to be anticipated, given Mars's greater distance from the Sun. As a planet positioned further out in the solar system's intricate ballot, its orbital path is naturally more expansive, requiring a greater stretch of time to complete a single grand revolution. Yet, despite this longer year and its increased solar distance, a deeper, more profound similarity emerges when we contemplate the celestial mechanics that govern Mars's seasonal cycles. Of all the planets that grace our solar system, Mars presents the most Earth-like seasonal variations. This remarkable congruence, this shared pattern of annual change, stems directly from the comparable tilts of the two planets' rotational axes. Earth's axis leans at approximately 23.5 degrees, a tilt that is largely responsible for the distinct and cherished progression of our four seasons. Mars, in a striking parallel, exhibits a rotational axis tilt of roughly 25 degrees. This close alignment, a mere 1.5-degree difference, is the cosmic architect behind the Martian seasons. What then are the profound implications of this axial kinship? It signifies, unequivocally, that Mars, much like Earth, experiences the ebb and flow of summers and winters. It endures the gradual warming and subsequent cooling of its hemispheres as it journeys through its elongated year. These seasonal shifts, however, on Mars, are far from uniform across its rugged, varied surface. The range of temperatures encountered during these different seasons can fluctuate quite dramatically, creating a mosaic of thermal extremes. Furthermore, the specific geographical location on the Martian surface can amplify or temper these variations, widening the overall spectrum of thermal conditions even further. For instance, at the planet's frigid polar winter caps, the temperatures can plummet to an astonishing low of approximately 43 degrees Celsius. This profound cold, a deep, pervasive chill, speaks to the raw, unbuffered nature of the Martian environment, particularly during the long, sunless periods of its polar winters. Conversely, as one ventures towards the equatorial regions during the Martian summer, the temperatures can, surprisingly, ascend to a comparatively balmy 35 degrees Celsius. This stark contrast, this swing from extreme frigidity to a warmth that could, momentarily, evoke thoughts of an arid desert underscores the dynamic and often harsh thermal landscape of our red neighbor. Indeed, Mars, mirroring Earth, possesses its own majestic polar caps. During the extended, continuous darkness of each pole's winter, a phenomenon, again, reminiscent of our own planet's polar regions, the temperatures plunge to such an extreme, such an unimaginable degree of cold, that a truly remarkable process unfolds. The very atmosphere in these hyper-chilled regions begins to freeze, literally transforming into solid slabs of carbon dioxide ice. These crystalline formations, these ethereal, frozen atmospheric remnants, accumulate silently, layer upon the surface of the planet's permanent polar caps. It is crucial to note, however, that these permanent caps themselves are not, predominantly, composed of this ephemeral CO2 ice. Instead, their enduring substance, their fundamental, foundational mass, is comprised overwhelmingly of water ice, a testament to the planet's deeper, more ancient hydrological history. The CO2 ice that forms seasonally acts as a temporary, shimmering veneer atop this more ancient, more substantial reservoir of frozen water. Observing these polar caps across the Martian year reveals a captivating, dynamic spectacle. The ice at both poles exhibits a pronounced, seasonal waxing and waning, a rhythmic expansion and contraction that mirrors, in a grand, planetary scale, the breathing of a living world. During the deepest throes of winter, the caps swell, their icy boundaries creeping outwards across the landscape as more atmospheric CO2 succumbs to the cold and precipitates onto the surface. Then, as spring advances and the sun's rays grow incrementally stronger, this temporary CO2 ice begins its ethereal retreat, sublimating directly back into the thin Martian atmosphere, revealing once again the underlying, more permanent water ice cap, now reduced in its visible expanse. This cyclical dance of freezing and sublimation offers a powerful, visual demonstration of the profound seasonal shifts that define the Martian year. Beyond the sheer scale and the dynamic nature of these polar caps lies an even more intriguing and visually stunning phenomenon: the presence of strange, almost mesmerizing, spiral patterns etched into the ice itself. Both the northern and southern poles display these exquisite, labyrinthine spirals, a testament to subtle, yet powerful, atmospheric forces. Scientists, in their quest to unravel these cosmic enigmas posit that these beautiful, intricate designs are the direct consequence of the Coriolis effect. This same inertial force, born of planetary rotation, that influences the direction of ocean currents and the swirling patterns of hurricanes, here on Earth, is thought to be the grand sculptor of these Martian ice spirals. It gently, yet persistently, nudges the moving atmospheric gases, creating a subtle, rotational influence that imprints itself onto the freezing and sublimating ice. The carbon dioxide ice, however, that adorns the poles does not, in its entirety, remain perpetually frozen. Its transient nature, its capacity for transformation, has a significant, cascading impact upon another vital aspect of the Martian environment: its winds. As the dry ice at the poles begins its profound metamorphosis from solid directly to gas, a process known as sublimation, it generates a remarkable and often violent atmospheric response. This rapid, localized release of vast quantities of gas can instigate truly enormous wind speeds, gusting with ferocious intensity at velocities reaching up to an astonishing 400 kilometers per hour. These powerful, sublimation-driven winds act as a potent geological agent, exerting a profound and tangible impact upon the ubiquitous dust that blankets much of Mars's surface. They are the unseen hands that sculpt the dunes, that whip up the planet, spanning storms, and that, in their ceaseless motion, slowly, yet inexorably, reshape the very face of this ancient world. We will delve deeper into the mesmerizing and sometimes terrifying intricacies of this dust-laden landscape and the colossal storms it spawns later in our journey as we continue to peel back the layers of Mars's captivating story. While the similarities between Mars and Earth, in terms of day length and seasonal tilt, are undeniably intriguing, it is equally important to acknowledge, and indeed, to marvel at, the profound and numerous differences that distinguish these two planetary neighbors. These disparities, these fundamental variations between our pale blue dot and the desolate red world, play a crucial role in shaping the unique and often challenging conditions that define the Martian environment. Firstly, and perhaps most obviously, Mars is significantly smaller than Earth. Its diameter, a mere 6,779 kilometers, pales in comparison to Earth's more substantial girth, which measures approximately 12,742 kilometers across. This difference in scale, this fundamental reduction in planetary mass, has direct and far-reaching consequences. Not only is Mars smaller, but it is also considerably less dense than our home planet. This reduced density, this more ethereal composition, directly translates to a gravitational pull at its surface that is markedly weaker than the gravitational embrace we experience here on Earth. To truly grasp the profound implications of this diminished gravity, let us conjure a vivid and illustrative example. Imagine, for a moment, an object, let us say, a simple spherical stone released from a height simultaneously on both Earth and Mars. On Earth, the stone would accelerate downwards with a familiar, brisk urgency, reaching the ground in a matter of moments. On Mars, however, the same stone would descend with a noticeably slower, more languid grace. This is due to the simple, yet profound, reality that Mars's gravitational pull exerts only about 38% of the force that Earth's gravity commands. In other words, the gravitational tug on Mars is a staggering 62% weaker than the powerful, grounding force we feel beneath our feet every single day. To put this into an even more personal perspective, consider your own weight. If you were to step onto a scale on the surface of Mars and your terrestrial weight measured a robust 100 kilograms, you would find yourself, astonishingly, weighing a mere 38 kilograms on the red planet. This dramatic reduction, this newfound lightness, is a testament to the profound influence of planetary mass and density on the fundamental force of gravity. Curiously, this specific gravitational pull, this exact percentage of Earth's gravity is almost precisely what one would experience on the innermost planet, Mercury. This is a fascinating, almost paradoxical equivalence, given that Mercury, with a diameter of only 879 kilometers, is considerably smaller in physical size than Mars. The subtle difference in their gravitational forces, with Mars's pull being only a marginal 1% stronger than Mercury's, serves as a powerful illustration of the critical role that density plays in determining a planet's gravitational might. It vividly demonstrates how much more densely packed the matter within Mercury's core must be in comparison to the more expansive, yet less substantial bulk of Mars. This weaker gravitational field, this gentler cosmic tether on Mars, has enabled the formation of some truly colossal and breathtaking geological features that would be utterly impossible to sustain under the more powerful, compressive grip of Earth's gravity. Among these planetary marvels, none stands quite so prominently, quite so majestically as Olympus Mons. This gargantuan shield volcano is not only the tallest volcano, but also the second tallest mountain in the entire solar system. Its only rival, in terms of sheer vertical prominence, is the imposing peak of Rhea Silvia located on the Vesta asteroid. However, some might argue that Rhea Silvia's claim to the title of tallest mountain is, perhaps, a slight technicality, a geological cheat, if you will. Rhea Silvia enjoys the distinct advantage of being situated at the very heart of an immense impact crater. Consequently, measurements of its towering height often commence from the very bottom of this deep, excavated basin, artificially inflating its perceived verticality. Olympus Mons, on the other hand, stands proudly on its own, a truly independent geological titan. Regardless of this subtle distinction, of Olympus Mons is nothing short of awe-inspiring. It rises to a staggering height that is 3 times the elevation of Earth's formidable Mount Everest when measured from its high point above sea level. While Everest, with its jagged, precipitous slopes, presents a dramatic and acutely steep profile, the edifice of Olympus Mons sprawls across an astonishing 600 kilometers in width. Its gentle, yet immense, flanks ascend gradually to an equivalent elevation of 22 kilometers above the Martian sea level, if such a concept could even be applied to this arid world. On Earth, a structure of such colossal proportions would simply be untenable. Our planet's stronger gravity would inexorably pull it down, causing its immense mass to collapse and spread out under its own formidable weight. The very reason a geological edifice of this magnitude can stand so proudly and so enduringly on Mars is precisely because its gravitational pull is, by comparison, so remarkably weak. It offers a lighter, more forgiving embrace, allowing such gargantuan formations to maintain their structural integrity across eons of Martian time. Olympus Mons, as previously mentioned, is classified as a shield volcano. This geological designation implies a specific and recognizable morphological characteristic, a very low, gradual profile. Its average slope is an incredibly gentle, mere 5 degrees. This remarkably shallow incline has a rather counterintuitive, yet profound implication. Were you to stand upon its immense summit, you would, in fact, be utterly unable to perceive the entire, sprawling mountain with your naked eye. The immense curvature of the planet itself would obscure its lower, more distant flanks, allowing only a localized view of its immediate surroundings. Despite its low profile, Olympus Mons is so gargantuan, so undeniably prominent, that it can be effortlessly discerned from the vast, silent expanse of space. If one were to consult a topographic map of Mars, its imposing form becomes strikingly evident, a vast, circular bulge on the planet's surface. To some, this immense, solitary peak might even conjure the whimsical image of a giant planetary pimple, a singular, raised blemish on the otherwise relatively smooth face of the red planet. At the very heart of this colossal volcano, one finds a series of collapsed craters, a complex, nested caldera, bearing silent witness to ancient and powerful eruptive events. The outer perimeter of the entire volcanic structure is delineated by a truly monumental cliff face, a sheer escarpment that can reach an astonishing height of up to 8 kilometers, a precipitous drop that would dwarf any terrestrial cliff. Another truly impressive and profoundly striking geological feature that carves its way across the side of the Martian globe like an immense, ancient scar is known as Valles Marineris. Every time one contemplates its sheer, unfathomable scale, a sense of profound, almost reverent amazement washes over the observer. This colossal canyon system stretches to an astonishing length that is 3 times the sprawling expanse of Earth's iconic Grand Canyon. Furthermore, its profound depths plunge to a staggering 4 times the vertical drop of its terrestrial counterpart. Valles Marineris is not merely a canyon, it is a monumental testament to the immense and often violent geological forces that have shaped and continue to shape the face of the red planet, a silent, enduring record of its deep planetary history. However, when one gazes upon the planet Mars, whether through the lens of a powerful telescope or in the vibrant clarity of high-resolution imagery, one of its most universally recognizable and indeed defining characteristics is its distinctive, pervasive color. The question then inevitably arises: why is the surface of Mars so strikingly, so unmistakably red? The answer to this fundamental query lies deep within the very composition of Mars's surface material. It all comes down to the abundant presence of large quantities of iron embedded within its ancient, weathered rocks and its omnipresent dust. Over the vast, incomprehensible stretches of geological time, these iron-rich minerals have engaged in a slow, yet inexorable, chemical tango with oxygen present in the planet's environment. This protracted interaction, this gradual yet profound process of oxidation, has led to the formation of iron oxide. To express this in a more relatable and terrestrial idiom, the entire planet has, quite literally, been slowly and methodically rusting across billions of years. This widespread, planetary-scale rusting is the direct and singular explanation for the characteristic reddish-brown hue that permeates the Martian ground and colors its scattered rocks. As we examine the countless photographs meticulously captured by the various robotic rovers dispatched by space agencies to Mars over the decades, the vivid, pervasive nature of this rust-colored landscape becomes strikingly apparent. Images like these, with their crisp resolution and profound clarity, possess an almost magical ability to transport us to the very surface of the red planet, allowing us to feel as if we are truly there, standing amidst its desolate beauty. Such visual fidelity, such an immersive sense of presence, would have been dismissed as an utterly impossible pipe dream for even the most visionary astronomers of a mere century ago. Thanks to the pioneering efforts and the enduring legacies of missions such as Viking 1 and 2, the Intrepid Spirit and Opportunity rovers, and more recently, the highly sophisticated Perseverance, we are afforded the extraordinary privilege of viewing Mars's arid, rust-stained vistas with an immediacy and a level of detail that feels as if they are spread directly before our very eyes. We can almost taste the fine dust, almost feel the ancient, silent winds that sweep across these magnificent, yet desolate, plains. However, after contemplating some of these stark, almost unearthly images, one might be tempted to conclude that the red planet is an entirely dead, geologically inert world. Yet, this initial impression, this quiet assumption, is, in fact, far from the actual truth. Mars is, surprisingly, a remarkably active planet, a dynamic sphere where a multitude of fascinating and often dramatic phenomena are constantly unfolding upon its surface. It is a world that, in its own unique way, pulsates with a subtle yet persistent geological vitality. Consider, for example, a truly astonishing event captured by an orbiting spacecraft in 2008, a massive avalanche. As the orbiter silently traversed its celestial path above the Martian surface, its cameras serendipitously recorded a sight that proved to be profoundly surprising to the scientists back on Earth. The imagery revealed an immense plume of dust billowing upwards into the thin atmosphere, unequivocally stirred by a colossal cascade of falling dirt and debris. What, precisely, were we witnessing in that captured moment? The avalanche occurred within a field of monumental, towering dunes, some of which reach an astonishing height of up to 700 meters. The particular image that documented this event spanned approximately 4 meters in width, providing a sense of the immediate scale. From this perspective, it becomes strikingly clear that the dust cloud unleashed by the tumbling mass was, by no means, a small, localized puff. Instead, it was a substantial, visually arresting phenomenon, a powerful demonstration of the dynamic and often violent forces that continue to reshape the Martian landscape. And here, take a closer look at another truly bizarre and captivating Martian marvel. Did you know that seemingly spider colonies emerge upon the surface of Mars? For those among us who harbor a deep-seated arachnophobia, there is, thankfully, no need for alarm. These peculiar, creepy, crawly shapes, which can stretch to an impressive 45 meters or even a full kilometer across, are not, in fact, true biological spiders. Instead, they are the ephemeral, yet striking, manifestations of warmed carbon dioxide ice, a testament to the unique interplay of sunlight and frozen atmospheric gases on the red planet. As the Martian spring gradually unfolds, the sunlight begins to penetrate and gently warm the layers of carbon dioxide ice that lie beneath the surface. This subterranean warming triggers a remarkable transformation. The solid ice reverts directly back into its gaseous form, a process, as we've discussed, known as sublimation. As this gas accumulates beneath the frozen crust, it builds an increasing internal pressure. Eventually, this trapped gas, unable to be contained any longer, bursts forth with explosive force through the overlying ice, which can be as much as 1 meter thick on its journey back into the thin Martian atmosphere. This sudden, powerful eruption of gas manifests as a large, geyser-like explosion, propelling dark, subsurface material upwards into the air. As this material then settles and disperses across the icy landscape, it creates the distinctive, radiating, spider-like patterns that have so intrigued and puzzled observers. These captivating images, these transient yet profound imprints of Martian geological activity, were recently captured by the European Space Agency's ExoMars Trace Gas Orbiter as it gracefully flew over the Martian surface in early 2024. They offer a vivid and often beautiful glimpse into the subtle yet powerful seasonal changes that continuously sculpt the face of Mars. Another compelling illustration of the dynamic nature of the Martian surface is provided by observing a specific dune that has been meticulously photographed on multiple occasions over the course of an entire Martian year. These sequential images reveal, quite strikingly, that the dune undergoes considerable and observable changes over this period. Ridges, for instance, that might have been subtle or indistinct in earlier observations become progressively more apparent as the ceaseless action of the Martian winds gradually wears away and redistributes the overlying dust. This continuous erosion and deposition of fine particles constantly re-sculpts the delicate contours of the dune, creating a living, evolving landscape. We have also seen, throughout our exploration, numerous images showcasing fresh impact craters. In these striking visuals, the raw power of the cosmic collision is vividly apparent, with plumes of dust clearly kicked up and scattered across the surrounding terrain by the force of the impact. One particular crater, however, stands out as especially interesting due to a unique and rather profound consequence of the celestial strike. In this instance, after the initial impact, the ground, rich in water ice, experienced a localized melting. The resulting liquid water then flowed for a brief period across the surface, leaving behind an unmistakable, meandering trail as it moved away from the immediate vicinity of the impact crater. The colors used in the imagery that depicts this phenomenon are, it must be noted, merely illustrative, serving to highlight the varying depths and topographical features of the flow. They do not represent the actual, true colors of the Martian soil in that specific location. While the Martian surface is undeniably awe-inspiring, a canvas of desolate beauty to behold, its visual appreciation is sometimes rendered more challenging than one might initially imagine. This difficulty, this periodic obscuration of its magnificent vistas, is largely attributable to Mars's pervasive and often overwhelming dust storms. When the planet's notoriously fast winds sweep with unbridled intensity across its dry, dusty surface, they effortlessly lift and suspend vast quantities of loose particulate matter from the ground. This airborne dust accumulates into colossal, towering walls, immense atmospheric phenomena that can, with astonishing speed, traverse and engulf the entire planet. It is sometimes genuinely challenging to fully grasp the sheer, monumental scale of these atmospheric behemoths. These storms, however, are so vast, so undeniably prominent, that they can be observed with remarkable clarity, even from the distant vantage point of space. Consider, for instance, a particularly striking example: a global dust storm meticulously captured by orbiting spacecraft in 2012. The initial imagery reveals a planet shrouded in a thick, pervasive haze, its distinctive reddish hue largely obscured by the churning, airborne dust. Then, just a week later, as the storm's fury gradually begins to subside, a dramatic and undeniable difference becomes apparent as the planet's features slowly re-emerge from beneath the dissipating veil. In another compelling photograph, if one directs their gaze towards the North Pole of Mars, a distinct, swirling storm is clearly visible, having swept across the uppermost reaches of the planet. Global dust storms on Mars are phenomena unlike anything we ever experience here on Earth. Their immense scale, their planet-spanning reach, and their profound impact on the Martian environment render them truly fascinating subjects of scientific inquiry. As we continue our exploration of Mars's dynamic surface, we encounter yet another remarkably intriguing and often visually stunning phenomenon. What, do you suppose, is the underlying cause of these intricate, often sinuous patterns that crisscross the Martian landscape almost as if etched by an unseen hand? The answer, surprisingly, lies in the frequent and often powerful activity of dust devils. These miniature tornadoes, these swirling columns of dust-laden air, are, in fact, surprisingly common on Mars. They have been meticulously photographed on countless occasions by both orbiting spacecraft and the intrepid rovers exploring the surface. From the elevated perspective of an orbiter, we can clearly discern the towering plumes of these Martian dust devils casting long, slender shadows across the sun-drenched plains. It is estimated that some of these plumes can reach an astonishing height exceeding 800 meters, with a considerable thickness of approximately 30 meters. The shadows they cast are equally impressive, stretching for about 2 kilometers across the surface, a vivid testament to their vertical prominence. Furthermore, we are incredibly fortunate to possess actual film footage captured from the perspective of a rover, documenting these powerful, swirling columns as they meander and drift across the Martian terrain. These rare and captivating, moving images offer an unparalleled glimpse into the dynamic and often visually spectacular world of Martian weather phenomena. One might, quite reasonably, assume, given the extensive discussion of atmospheric phenomena such as colossal dust storms and ubiquitous dust devils, that Mars possesses an atmosphere that is, in some way, comparable to the dense, life-sustaining envelope that surrounds our own planet, Earth. However, this assumption would be entirely incorrect. The reality of the Martian atmosphere is profoundly different, a stark, almost unimaginable contrast to the vibrant, breathable air we take for granted. To truly appreciate the profound thinness of Mars's atmospheric veil, let us engage in a vivid, comparative thought experiment. Imagine for a moment that we are soaring here on Earth at an altitude of approximately 38,000 feet, high above the ground level. At this elevation, the air is already exceptionally thin, significantly less dense than at sea level. If, hypothetically, one were to exit the confines of an aircraft at this dizzying height, not only would the inevitable and fatal fall ensue, but the individual would also struggle desperately for breath along the way. The air at such an altitude simply lacks the necessary density to sustain human respiration without specialized equipment. Now, consider Mars. The atmospheric conditions on the red planet are, in fact, even more extreme, even more profoundly attenuated. To encounter a similar level of atmospheric pressure as that found on the surface of Mars, one would need to ascend to an astonishing altitude, here within Earth's own atmosphere, reaching approximately 120,000 feet. This stark comparison, this almost unbelievable disparity, underscores the profound emptiness, the vacuum-like quality of the Martian atmosphere. The challenge of breathing on Mars is further exacerbated by the very composition of this thin atmospheric envelope. An overwhelming 96% of the Martian atmosphere consists of carbon dioxide. This makes it utterly unbreathable for humans, even if the pressure were somehow miraculously increased. Consequently, any aspiring visitor to the red planet would be compelled to wear a meticulously sealed and robust pressure suit, providing not only a breathable, oxygen-rich environment, but also protection against the near-vacuum conditions and the extreme temperatures. Thankfully, however, the profound thinness and the unbreathable composition of Mars's atmosphere do not, in any way, preclude the occurrence of truly spectacular and profoundly beautiful celestial phenomena. Indeed, Mars, despite its desolate nature, is renowned for its absolutely stunning sunsets. Some of these ethereal twilight spectacles have been serendipitously captured by the very rovers diligently exploring the Martian surface, offering us a glimpse of a beauty that transcends planetary differences. The way the thin, dust-laden atmosphere scatters the dying light of the distant sun creates a palette of blues and purples unlike anything seen on Earth, a testament to the unique optics of this alien world. The current, low atmospheric pressure on Mars and its accompanying profound thinness was not, however, always the prevailing condition. Geological evidence etched across the Martian landscape speaks eloquently of a far different and more clement past. The undeniable presence of ancient, dry riverbeds, winding their way across the planet's surface, provides compelling and indeed irrefutable proof that Mars's atmosphere was once considerably thicker and far more substantial. This more robust atmospheric envelope would have been sufficiently dense to retain the necessary heat and to exert the requisite pressure that would have allowed liquid water to flow freely and abundantly across its surface. This vision of a watery, ancient Mars stands in stark contrast to the arid, frozen desert we observe today. The critical question, then, arises: where did that once thicker, life-sustaining atmosphere ultimately disappear? scientists, in their diligent pursuit of answers, largely converge on a single, compelling explanation: Mars's magnetosphere, or rather, its profound and ancient lack thereof, is deemed to be the primary culprit. It is widely believed that Mars, tragically, lost its protective global magnetosphere, an immense, invisible shield that would have deflected the relentless onslaught of solar winds approximately 4 billion years ago. This catastrophic loss, this stripping away of its planetary defense, left Mars utterly vulnerable to the ceaseless, energetic particles emanating from the Sun. Unimpeded, these powerful solar winds were then free to relentlessly strip away, atom by atom, the vital constituents of Mars's upper atmosphere, gradually eroding its precious gaseous envelope into the vacuum of space. This slow, inexorable process, unfolding over billions of years, transformed Mars from a potentially habitable world into the desolate, thin-aired planet we observe today. Indeed, some of the orbiting spacecraft diligently studying Mars have, on occasion, directly detected these ionized atmospheric particles trailing off into the vast emptiness of space behind the planet. These ghostly plumes, these escaping remnants, serve as a poignant and direct observation of the very process that fundamentally reshaped the destiny of the Red Planet. They are silent, yet eloquent, witnesses to the profound and irreversible atmospheric escape that has characterized Mars's long and often tragic planetary history. One of the final, yet equally captivating aspects of Mars that warrants our focused attention, and indeed our quiet contemplation, are its two enigmatic moons Phobos and Deimos. These celestial companions, these silent sentinels orbiting their rust-colored parent world, are in stark contrast to our own solitary and majestic moon, remarkably small and distinctively irregularly shaped. They are, in essence, little more than captured asteroids, celestial wanderers drawn into Mars's gravitational embrace eons ago. Their diminutive size is truly striking. If one were to gaze upwards into the Martian night sky, the apparent size of these moons would be astonishingly small, almost insignificant, in comparison to the grand, luminous disk that our own moon presents to Earth's observers. Phobos, though the larger of Mars's two satellites, still appears relatively modest in the Martian firmament. However, even this apparent size is, in a subtle way, somewhat misleading, for Phobos is positioned in an orbit that is dramatically closer to Mars than Earth's moon is to our planet. To put this into a more tangible perspective, our familiar moon maintains an average distance of approximately 384,400 kilometers from Earth. Phobos, by contrast, hurtles around Mars at a mere 6,000 kilometers from its surface. This astonishing proximity is roughly equivalent to the distance between London and New York, a mere stone's throw in cosmic terms. It might be genuinely surprising to realize just how vast the expanse of space truly is between Earth and its moon. One could conceivably fit several Earth-sized planets within that immense void. Yet, between Mars and its innermost moon, Phobos, there is barely enough room to squeeze in a single Mars-sized sphere. This close gravitational embrace has profound implications for Phobos's future, as we shall soon quietly contemplate. Deimos, the other Martian moon, is, on the other hand, even smaller than Phobos and orbits at a considerably greater distance from Mars. Consequently, when viewed from the Martian surface, Deimos would appear little more than a distant star, a tiny luminous point, slowly, almost imperceptibly, tracing its orbital path across the planetary canvas. Despite their diminutive stature and their somewhat irregular forms, it is difficult not to agree that these two moons possess a quiet, unassuming beauty, a charm that is entirely their own, as they silently, yet steadfastly, accompany Mars on its long journey through the solar system. And our exploration of these tiny, yet captivating, Martian moons is not yet complete. There is a phenomenon, a truly breathtaking spectacle, that, when first encountered, evokes an almost childlike sense of absolute amazement. Imagine, for a moment, witnessing a solar eclipse caused by Phobos, meticulously captured by one of the intrepid rovers diligently exploring the surface of Mars. For many of us, the rare and often fleeting experience of a solar eclipse here on Earth is itself a profound and memorable event. To witness such a cosmic alignment from an entirely different planet is, quite simply, something else entirely, a unique and unparalleled astronomical privilege. In these remarkable images, we are granted an intimate view of Phobos in all its irregular, rocky glory as it gracefully, yet swiftly, traverses the fiery disk of the Sun. Its uneven silhouette, its rugged, asteroid-like contours, are sharply defined against the brilliant solar backdrop. It is particularly interesting to observe the subtle, yet discernible effect this transit has upon the ambient lighting in the immediate vicinity of the rover. As Phobos passes, a perceptible dimming, a soft, transient darkening descends upon the landscape, a fleeting echo of the immense, celestial ballot unfolding high above. These moments, these glimpses of cosmic grandeur remind us of the profound and interconnected wonders that permeate our vast and silent solar system. The pursuit of knowledge, the tireless quest for answers to the profound and often complex questions that Mars so eloquently poses, can be an arduous and challenging endeavor. Yet, on our home planet, Earth, a different kind of data, a different kind of information is meticulously collected, often without our explicit knowledge, or indeed our direct consent. This information, gathered by entities known as data brokers, pertains not to celestial bodies, but to our own personal lives. These brokers compile and subsequently sell this deeply personal data to any party willing to purchase it, all within the bounds of legality. While they are legally obligated to remove your information should you formally request it, they often intentionally render the process incredibly difficult and frustratingly opaque, a labyrinthine bureaucratic maze. Fortunately, however, in our increasingly interconnected and often vulnerable digital world, there exist modern-day guardians dedicated to safeguarding our personal privacy. Turning our attention back to Mars and the grand, ambitious timeline envisioned by space agencies, a truly transformative era lies just on the horizon. Within the span of the next decade, a monumental achievement, once confined to the vivid imaginings of science fiction, is poised to become a tangible reality. The first human feet are likely to touch down upon the dusty, crimson soil of Mars. This bold, yet meticulously planned, timeline is not, by any stretch, unrealistic. It is a testament to decades of tireless innovation and the unwavering dedication of countless scientists and engineers. While that inaugural visit, that initial awe-struck moment of human presence on Mars, might, in its early stages, bear a resemblance to the historic moon landings, a brief, exploratory stop, a fleeting, yet profound, demonstration of human capability. The long-term vision extends far beyond mere visitation. Indeed, some visionary scientists are already asserting, with a quiet confidence, that permanent human colonies, self-sustaining outposts, could be established on Mars as early as the year 2050. This means, with a sense of profound, almost surreal possibility, that it could, very well be, individuals alive today, perhaps even those quietly watching this very video, who might one day embark upon that monumental journey to tame and settle this new frontier world. Should this future unfurl as envisioned, a swift and decisive immersion into a rigorous space program would, of course, be an imperative for any aspiring Martian colonizer. But the profound possibility, the tantalizing prospect, remains that you, or someone you know, might one day gaze out from a small bay window on an alien world and watch as our familiar, pale blue dot Earth gradually recedes, shrinking into a distant, almost imperceptible speck against the infinite, black canvas of space. But as your gaze then turns towards your new, rust-colored home, what precise conditions, what formidable challenges can you, as a would-be Martian, expect to encounter? What fundamental hurdles must any prospective colonizer meticulously overcome? What deadly, unpredictable weather phenomena will the red planet relentlessly hurl in your path? For unlike our vibrant, life-teeming home planet, Mars, in its current state, is largely a dead world, a desolate, unforgiving expanse. Any individual, or indeed any group, hoping to establish a lasting foothold upon its barren surface will need to confront and ultimately conquer its daunting and often hostile challenges, armed with technology that stands at the very cutting edge of human ingenuity. The journey itself to reach Mars is, of course, the indispensable first step in any colonization endeavor. With optimal launch conditions aligning the orbital paths of Earth and Mars, this cosmic voyage would typically span a duration of approximately 3 months. On the surface, this might not appear excessively long, perhaps comparable to a protracted voyage on a terrestrial cruise ship, a period of extended yet contained travel. However, a crucial and often overlooked factor demands careful consideration. For the entirety of those 3 months, and potentially longer, you would be spending that considerable duration outside the protective embrace of Earth's powerful, global magnetic field. In the vast, unfiltered expanse of interplanetary space, beyond the shielding effects of our planet's magnetosphere, you would be relentlessly exposed to the harsh and often dangerous onslaught of the solar wind and the pervasive, insidious threat of cosmic radiation. Prolonged exposure to these energetic particles, these unseen hazards, poses significant and deeply concerning health risks to astronauts. Such radiation has been directly linked to an increased likelihood of developing various forms of cancer, and, even more disturbingly, to the premature onset of symptoms akin to Alzheimer's disease, long before the wary travelers even reach their Martian destination. Fortunately, however, scientists and engineers are not oblivious to these profound dangers. Considerable thought and innovative research are being dedicated to devising ingenious methods for protecting future Martian pioneers from this relentless cosmic bombardment. One promising avenue of defense involves the strategic utilization of materials rich in hydrogen within the very construction of the spacecraft itself. Hydrogen, with its singular proton, is exceptionally effective at attenuating the harmful effects of radiation. Indeed, a particularly elegant solution proposes surrounding the astronaut's living and working cabin with a substantial water tank, integrated directly into the ship's walls. Water with its abundant hydrogen content would serve as an effective and readily available radiation shield. Another, more technologically ambitious option involves the creation of an artificial magnetic field encompassing the spacecraft. This concept, however, presents its own formidable challenges, primarily the immense energy requirements necessary to generate such a powerful protective field. It would necessitate the development of a compact, yet extraordinarily potent, reactor small enough to be safely integrated within the confines of the spacecraft. As of now, the technology to achieve this, with the requisite levels of safety and efficiency, remains just beyond our current grasp, a future aspiration, rather than a present-day reality. Once the arduous journey is successfully completed and the first human settlers arrive at their crimson destination, they will discover that for an alien planet, cloaked in such a stark, reddish mantle, Mars is, surprisingly, not as profoundly foreign as one might initially conceive. There are, as we have touched upon, echoes, subtle yet persistent, of our terrestrial home woven into the very rhythm of its cosmic existence, offering a semblance of familiarity amidst the profound alienness. One of the most striking, and perhaps comforting, of these resemblances lies in the fundamental measurement of a day. The solar day on Mars, known as a sol, unfurls itself in a duration that is only marginally, incrementally longer than the familiar 24-hour cycle we experience here on Earth. To be precise, a Martian day extends to 24 hours, 39 minutes, and 35 seconds. This slight elongation, a mere whisper of additional time, allows for a familiar, almost parallel cadence to daily existence, a subtle cosmic synchronicity that might, one day, provide a small comfort to future human inhabitants. However, when we turn our attention to the Martian year, the disparity becomes somewhat more pronounced. The annual journey of Mars around its parent star, the Sun, stretches considerably beyond our own 365-day terrestrial orbit. A full Martian year encompasses approximately 1.88 Earth years, or when broken down into a more tangible measure, it equates to 1 year, 320 days, and approximately 80.2 hours. This extended orbital period, this longer, more languid celestial dance, is, of course, entirely to be anticipated given Mars's greater distance from the Sun. As a planet positioned further out in the solar system's intricate ballot, its orbital path is naturally more expansive, requiring a greater stretch of time to complete a single grand revolution. Yet, despite this longer year and its increased solar distance, a deeper, more profound similarity emerges when we contemplate the celestial mechanics that govern Mars's seasonal cycles. Of all the planets that grace our solar system, Mars presents the most Earth-like seasonal variations. This remarkable congruence, this shared pattern of annual change, stems directly from the comparable tilts of the two planets' rotational axes. Earth's axis leans at approximately 23.5 degrees, a tilt that is largely responsible for the distinct and cherished progression of our 4 seasons. Mars, in a striking parallel, exhibits a rotational axis tilt of roughly 25 degrees. This close alignment, a mere 1.5-degree difference, is the cosmic architect behind the Martian seasons. What then are the profound implications of this axial kinship? It signifies, unequivocally, that Mars, much like Earth, experiences the ebb and flow of summers and winters. It endures the gradual warming and subsequent cooling of its hemispheres as it journeys through its elongated year. These seasonal shifts, however, on Mars, are far from uniform across its rugged, varied surface. The range of temperatures encountered during these different seasons can fluctuate quite dramatically, creating a mosaic of thermal extremes. Furthermore, the specific geographical location on the Martian surface can amplify or temper these variations, widening the overall spectrum of thermal conditions even further. For instance, at the planet's frigid polar winter caps, the temperatures can plummet to an astonishing low of approximately 43 degrees Celsius. This profound cold, a deep, pervasive chill, speaks to the raw, unbuffered nature of the Martian environment, particularly during the long, sunless periods of its polar winters. Conversely, as one ventures towards the equatorial regions during the Martian summer, the temperatures can, surprisingly, ascend to a comparatively balmy 35 degrees Celsius. This stark contrast, this swing from extreme frigidity to a warmth that could, momentarily, evoke thoughts of an arid desert, underscores the dynamic and often harsh thermal landscape of our red neighbor. Indeed, Mars, mirroring Earth, possesses its own majestic polar caps. During the extended, continuous darkness of each pole's winter, a phenomenon, again reminiscent of our own planet's polar regions, the temperatures plunge to such an extreme, such an unimaginable degree of cold, that a truly remarkable process unfolds. The very atmosphere in these hyper-chilled regions begins to freeze, literally transforming into solid slabs of carbon dioxide ice. These crystalline formations, these ethereal, frozen atmospheric remnants, accumulate silently, layer upon layer, upon the surface of the planet's permanent polar caps. It is crucial to note, however, that these permanent caps themselves are not, predominantly, composed of this ephemeral CO2 ice. Instead, their enduring substance, their fundamental, foundational mass, is comprised, overwhelmingly, of water ice, a testament to the planet's deeper, more ancient hydrological history. The CO2 ice, that forms seasonally, acts as a temporary, shimmering veneer atop this more ancient, more substantial reservoir of frozen water. Observing these polar caps across the Martian year reveals a captivating, dynamic spectacle. The ice, at both poles, exhibits a pronounced, seasonal waxing and waning, a rhythmic expansion and contraction that mirrors, in a grand, planetary scale, the breathing of a living world. During the deepest throes of winter, the caps swell, their icy boundaries creeping outwards across the landscape as more atmospheric CO2 succumbs to the cold and precipitates onto the surface. Then, as spring advances and the sun's rays grow incrementally stronger, this temporary CO2 ice begins its ethereal retreat, sublimating directly back into the thin Martian atmosphere, revealing, once again, the underlying, more permanent, water ice cap, now reduced in its visible expanse. This cyclical dance of freezing and sublimation offers a powerful, visual demonstration of the profound, seasonal shifts that define the Martian year. Beyond the sheer scale and the dynamic nature of these polar caps lies an even more intriguing and visually stunning phenomenon: the presence of strange, almost mesmerizing, spiral patterns etched into the ice itself. Both the northern and southern poles display these exquisite, labyrinthine spirals, a testament to subtle, yet powerful, atmospheric forces. Scientists, in their quest to unravel these cosmic enigmas, posit that these beautiful, intricate designs are the direct consequence of the Coriolis effect. This same inertial force, born of planetary rotation, that influences the direction of ocean currents and the swirling patterns of hurricanes here on Earth, is thought to be the grand sculptor of these Martian ice spirals. It gently, yet persistently, nudges the moving atmospheric gases, creating a subtle, rotational influence that imprints itself onto the freezing and sublimating ice. The carbon dioxide ice, however, that adorns the poles does not, in its entirety, remain perpetually frozen. Its transient nature, its capacity for transformation, has a significant, cascading impact upon another vital aspect of the Martian environment: its winds. As the dry ice at the poles begins its profound metamorphosis from solid directly to gas, a process known as sublimation, it generates a remarkable and often violent atmospheric response. This rapid, localized release of vast quantities of gas can instigate truly enormous wind speeds, gusting with ferocious intensity at velocities reaching up to an astonishing 400 kilometers per hour. These powerful, sublimation-driven winds act as a potent geological agent, exerting a profound and tangible impact upon the ubiquitous dust that blankets much of Mars's surface. They are the unseen hands that sculpt the dunes, that whip up the planet, spanning storms, and that, in their ceaseless motion, slowly yet inexorably reshape the very face of this ancient world. This extraordinary phenomenon, the sublimation of dry ice, and its subsequent generation of immense wind speeds, is in fact the primary catalyst behind one of the most unique, and indeed terrifying, aspects of Martian weather: its colossal, planet-engulfing dust storms. If one were to simply peer across the rusted ochre surface of Mars through the serene and often static lens of photographic imagery, one would be entirely forgiven for forming the impression that this distant world is a place of profound stillness. Flat, dusty landscapes would appear to stretch interminably in all directions, broken only by scattered rocky outcrops, and perhaps the faint, ethereal whistling of a thin, anemic wind serving to keep at bay the almost oppressive and all-encompassing solitude. Yet, were one to linger for a more extended period upon this red, desolate world, a dramatic and awe-inspiring transformation would eventually unfold. One would inevitably witness the slow yet inexorable brewing on the distant horizon of a towering, immense wall of dust and fine sand, an ominous harbinger of meteorological upheaval. An initial, human inclination might be to compare this approaching dust storm to the similar, yet vastly different phenomena we occasionally observe here on Earth. However, such a comparison would be deeply misleading, for one would have no conceivable idea of the truly monumental scale to which this Martian storm is poised to escalate. This particular storm would not merely expand to encompass a single region or even an entire continent. Instead, its thick, choking dust would swell and spread with terrifying rapidity until it had entirely swallowed up not just a localized area, but the vast, sprawling expanse of the entire planet. This all-enveloping global superstorm, a meteorological titan, typically arises on Mars with a predictable yet formidable regularity, usually once every 3 Martian years, which translates to approximately 5.5 Earth years. Its dense, pervasive dust would effectively blot out the precious light from the distant sun for weeks or even for months on end. Such a prolonged and intense obscuration of sunlight represents a colossal and indeed an existential challenge to the continued functionality of any technology that humanity has dared to deploy upon the Martian surface. Furthermore, if humans ever hope to establish enduring settlements upon the Red Planet, these recurring planet-spanning storms will present a formidable hurdle, a profound obstacle that must, unequivocally, be understood and ultimately overcome. This, however, is compounded by a critical deficiency in our current knowledge much about the precise origins and the intricate dynamics of these immense storms remains tantalizingly unknown to us. It is worth noting that Mars, in its ancient geological past, did not always have to contend with such colossal planet-sized dust storms. Although Mars, in its current epoch, presents itself as a barren, arid, and desolate planet, geological evidence, as we've discussed, unequivocally indicates that it once possessed a considerably thicker atmosphere. This more substantial and more robust, gaseous envelope was, crucially, warm enough to support the widespread existence of running liquid water flowing freely across its surface. However, over the course of billions of years of its long and often dramatic planetary existence, Mars gradually and inexorably dried out. Its once thicker atmosphere steadily bled away into the vacuum of space until its current atmospheric volume plummeted to less than 1% of the vibrant, life-sustaining atmosphere we cherish here on Earth. Yet, these immense, planet-spanning dust storms did not simply spontaneously begin solely because Mars became a dry and arid world. While our understanding of the precise origins of such colossal storms remains incomplete, we strongly assume that a key and indispensable contributing factor is the planet's temperature. With a significantly thinner atmosphere, Mars, despite its relatively high concentrations of carbon dioxide, became far less efficient at retaining any absorbed heat. When the Martian surface begins to cool, there is simply an insufficient quantity of atmospheric gas to effectively trap and redistribute the escaping warmth. This inefficiency in heat retention leads to a truly remarkable and often extreme thermal phenomenon. If, hypothetically, you were to stand upon the planet's equator during its warmest time of day, your feet, directly in contact with the sun-warmed ground, might experience a comparatively comfortable 23 degrees Celsius. Yet, simultaneously, your head, merely a few feet higher, would be enveloped in air that is a frigid 0 degrees Celsius. This stark vertical temperature gradient, this profound difference between ground level and a mere meter or two above it, speaks to the atmosphere's inability to homogenize and circulate heat effectively. As mentioned earlier, this also means that between the Martian day and the Martian night, there are some truly intense and often dangerous temperature swings, further exacerbating the challenges of maintaining a stable, hospitable environment. These significant temperature differences, these thermal gradients, are, of course, the fundamental drivers behind the formation of winds, which, in turn, can propel various weather systems across a planetary body. However, on Mars, the arid and often violent weather patterns are no longer primarily driven by the familiar cycles of rain and water as they are on Earth. Instead, the Martian weather, and particularly its most formidable storms, are now almost entirely dictated by intricate cycles of dust. Dust on Mars plays a surprisingly crucial, and indeed an indispensable, role. Without its omnipresent influence, those immense, planet-spanning storms would, in all likelihood, never even form, while the thin Martian atmosphere may be largely ineffective at capturing and transporting planetary heat. The Martian dust itself presents an entirely different and far more dynamic story. These ubiquitous particles, these finely ground remnants of ancient rock, possess a remarkable capacity for absorbing and subsequently radiating solar energy. It all begins with this Martian dust finding its way into the planet's thin, gaseous envelope. There are several primary mechanisms that facilitate this initial, crucial step. One of the most visually striking and frequently observed of these mechanisms involves the aforementioned dust devils. Mars, as we've learned, experiences thousands of these swirling, miniature tornadoes every single year, with a particular prevalence during the Martian spring and summer months. The process begins when the sun's warm, unfiltered rays directly heat the barren ground. This localized heating causes the air immediately adjacent to the surface to rise, creating an area of lower pressure. Consequently, cooler, denser air from the surrounding atmosphere is drawn downwards to fill this nascent vacuum. This dynamic interplay of contrasting winds initiates the formation of rising spirals of air, which, as they gain momentum, can expand into colossal columns, sometimes hundreds of meters wide, and reaching an astonishing 8.5 kilometers in height, although many are considerably smaller. Regardless of their specific dimensions, as these dust devils meander their way across Mars's vast, all-encompassing deserts, they act as powerful, natural vacuum cleaners. They voraciously suck up the fine, loose dust from the surface and hurl it upwards into the thin atmosphere. This continuous process creates a persistent haze, a subtle darkening of the Martian skies in their wake. This ongoing contribution from countless dust devils is thought to be a significant factor in maintaining a pervasive background layer of dust that constantly lingers within Mars's atmosphere, forming a subtle, yet omnipresent veil. While dust devils represent the most visually dramatic and perhaps the flashiest way by which dust enters the Martian atmosphere, they are, in fact, not the most prevalent mechanism. Far more common and equally crucial is the simple, yet ceaseless, influence of the wind moving across Mars's dusty surface, coupled with a fascinating and fundamental process known as saltation. Surprisingly, the fine Martian dust is, in its initial state, remarkably difficult to dislodge and lift into the air. These small particles possess a significant degree of cohesion, primarily due to their slightly electrostatic nature, a characteristic somewhat akin to the way packing peanuts tend to cling together. This inherent stickiness means that these fine dust particles require a certain critical amount of momentum, a decisive push, to overcome their mutual attraction and become airborne. Intriguingly, it is the slightly larger particles, the individual grains of sand, that are actually easier for the wind to set in motion as they experience less of this cohesive electrostatic force. So, it is these larger sand grains, these more substantial particles, that are initially lifted by gusts of wind and transported for short distances across the surface. However, because they are ultimately too heavy for the thin Martian wind to suspend them indefinitely in the atmosphere, they inevitably crash down again back onto the surface. The force of these countless, tiny impacts, these ceaseless collisions, imparts enough momentum to the smaller, more cohesive dust particles lying beneath to overcome their inherent stickiness and become airborne. This process of larger grains impacting and then dislodging finer dust is the essence of saltation, and it is a pervasive and critical mechanism for introducing dust into the Martian atmosphere. However, once this fine dust successfully gets up there into the thin Martian atmosphere, Mars's significantly lower gravity plays a crucial role. This reduced gravitational pull means that it is remarkably easy for these dust particles to remain suspended aloft for an exceptionally long duration. They can drift and circulate within the atmosphere for weeks or even for months on end. This prolonged atmospheric residence time for the dust is, in itself, a sufficient catalyst to begin driving the formation of those immense, planet-spanning storms. The critical factor here is that, unlike the thin, almost insubstantial air that surrounds them, these particles of dust are remarkably efficient at collecting and absorbing heat from the sun. As the distant sunlight warms the vast quantities of dust suspended in the atmosphere, these myriad particles act like countless, tiny radiators, slowly yet consistently releasing the gathered thermal energy into the surrounding air, where, previously, much of the sun's warmth would have passed through the thin atmosphere and been absorbed by the ground below. Now, the presence of airborne dust ensures that the atmosphere itself becomes significantly warmer. This warming of the atmosphere then initiates a familiar meteorological pattern: warm air rises. However, now, due to the widespread distribution and heat-absorbing properties of the dust, this rising air begins to do so on a much larger and more expansive scale than the localized updrafts that form during the creation of dust devils, which we discussed earlier. As this large mass of warm air ascends, it creates an area of low pressure, which in turn draws in more wind from the surrounding, cooler regions at the sides of the rising air mass. This influx of additional wind, however, only serves to add more fuel to the burgeoning atmospheric fire. More wind inexorably means more saltation and consequently more dust being relentlessly thrown into the atmosphere. This increased dust content then provides even more opportunities for the atmosphere to absorb and radiate solar heat, perpetuating and intensifying the warming cycle. Eventually, this out-of-control, positive feedback loop, this escalating process, rapidly ramps up from localized dust lifting into a full-blown, regional dust storm encompassing vast swaths of the Martian surface. The good news, for any hypothetical human observer caught within a local or even regional Martian dust storm, is that, on a purely localized scale, such an event is not inherently very dangerous in and of itself. The wind speeds within these storms typically top out at approximately 97 kilometers per hour. This velocity, while considerable, is in fact only about half the speed of hurricane-force winds that can devastate here on Earth. Moreover, even this measurement of wind speed can be somewhat misleading due to the profound thinness of the Martian atmosphere. Even when traveling at such seemingly rapid velocities, the actual physical impact or pushing power of the wind would be significantly less than one might intuitively expect on Earth. It's akin to the difference in pushing power between a single person and an entire crowd, despite both potentially moving at the same speed. The sheer lack of atmospheric density means the wind simply doesn't carry the same kinetic energy or exert the same force as its terrestrial counterparts. Therefore, contrary to what one might encounter in some dramatic, science fiction portrayals of Martian dust storms, these atmospheric phenomena are not, in fact, powerful enough to physically push over or topple spacecraft or to shatter delicate satellite dishes anchored firmly to the surface. However, this is not, by any means, to suggest that they cannot or do not cause significant and often mission-ending problems. The challenges they present, while not directly destructive, are insidious and deeply impactful, particularly for our robotic emissaries. Consider, for instance, the compelling and ultimately tragic case of a pioneering rover. On the 28th of June in 2007, a significant milestone in its extended mission, a period spanning 200 Martian days, this diligent rover was meticulously preparing itself for its descent into the captivating depths of Victoria Crater. However, just as it perched itself precariously atop the crater's formidable slope, an unforeseen and monumental event unfolded. The largest dust storm the rover had ever encountered during its long and illustrious mission began to roll in, with ominous speed, gradually engulfing the landscape. The immediate and most critical consequence of this immense storm was a dramatic reduction in the ambient brightness of the sun. The atmospheric dust became so thick, so pervasive, that it diminished the incoming solar radiation by an astonishing 96%. This figure, however, while seemingly dire, is not quite as catastrophically bad as it might initially sound. The suspended dust also had the effect of scattering a portion of the sunlight in various directions, including, fortuitously, towards the rover. This scattered light provided a small, yet crucial, amount of illumination. Consequently, even on the darkest day of the storm's peak, the rover was still generating approximately 128 watts of power, a stark contrast to its usual, robust 700 watts generated on a clear, unobstructed Martian day. Nevertheless, for a solar-powered rover like this one, even 128 watts was deeply problematic. That level of power generation was simply insufficient to keep the rover's vital systems operating sustainably. In fact, any power output falling below 150 watts meant that the onboard batteries would inevitably begin to run flat. Faced with this critical energy deficit, the rover's operations were drastically curtailed and scaled back to the bare essentials until the storm eventually subsided. The rover was commanded to communicate back to Earth only once every 3 days, conserving its precious, dwindling power. The implications of completely flat batteries were dire. The sensitive components on board the rover could be irreparably damaged due to the intense and wildly fluctuating cold temperatures that characterize the Martian night. Typically, the rover's motors and other critical systems were equipped with heaters powered by the batteries, designed to keep them warm and functional during the frigid nocturnal hours. If the batteries were to completely deplete, there would be no power to activate these heaters, leaving the components exposed to the extreme temperature differences between day and night. At the equator, for instance, temperatures can swing from a relatively mild 20 degrees Celsius during the day to a brutal 75 degrees Celsius at its coldest during the night. Such extreme thermal cycling would inevitably inflict severe damage upon the rover's delicate and sensitive internal components. As for the dust storm itself, mission controllers initially harbored the hope that its duration would be brief, perhaps only a week. However, by the 15th of July, the storm had reached its apex, its most intense and pervasive phase. True color images, captured in a time-lapse sequence, vividly illustrate the escalating severity of the storm revealing a landscape that progressively plunges into a profound and almost total darkness. Thankfully, however, the sheer severity of this particular dust storm, while alarmingly close, was not quite sufficient to trigger the rover's low power fault, which would have put it into a deep and potentially irreversible hibernation. It was a perilously close call, a period of intense anxiety for the mission team. Eventually, by the 21st of August, corresponding to Martian Day 1271, the storm had sufficiently cleared, allowing the rover to gradually and cautiously resume its forward movement and its scientific operations. It was a lucky turn of events, a fortunate reprieve for the diligent rover. However, not all robotic explorers dispatched to Mars have been so fortunate in their encounters with these formidable atmospheric behemoths. Indeed, at the close of that very same year, another pioneering rover, the sister craft to the one previously discussed, was facing far more serious and ultimately insurmountable problems. Martian storms in recent months had been escalating in both frequency and intensity, leaving its solar panels heavily and stubbornly covered with fine, pervasive dust. This pervasive coating, coupled with the atmospheric obscuration, meant that up to 99% of the incoming sunlight was being blocked from reaching its vital power source. Survival for this aging rover was becoming increasingly difficult, a precarious tightrope walk on the edge of its operational limits. Consequently, its scientific operations were now drastically reduced from its peak, a shadow of its former energetic self. At this critical juncture, the aging rover was generating a mere 128 watt-hours of power. As previously established, this figure fell significantly short of the 150 watt-hours required to simply keep itself warm and its delicate components protected during the frigid Martian nights. If the crucial heating systems were to fail, the rover's sensitive internal components would inevitably succumb to the extreme cold, leading ultimately to their irreversible failure. A glimmer of hope, however, emerged in the form of two small, fortuitous cleaning events. These localized gusts of wind, or perhaps small dust devils, managed to dislodge some of the accumulated dust from its solar arrays. This modest, yet crucial, clearing boosted the energy output of the solar panels to a more sustainable 372 watt-hours. This temporary surge in power provided the rover with enough energy to recharge its batteries and to cautiously begin to move again, a brief yet vital reprieve. But the relentless flow of time and the inexorable wear and tear of the Martian environment are always cruel, always persistent. The rover began to experience unexplained memory gaps in April 2009. With its operational life drawing to a close and now only 4 meters away from its designated resting place on Martian Day 1892, it encountered a critical and ultimately fatal setback. It drove into an incredibly soft, deep patch of dusty soil at a location that would forever be known as Troy, the site of its final valiant stand. Beneath its wheels lay a mineral known as jarosite, a type of iron sulfate. Jarosite possesses remarkably low cohesion, meaning that the rover's wheels, despite their desperate churning, were unable to achieve sufficient traction to extricate itself. Moving forward proved utterly impossible. Despite the tireless and ingenious efforts by the mission team back on Earth at the Jet Propulsion Laboratory to explore various techniques and simulations for escaping this treacherous sand trap, no meaningful progress could be made. On Martian Day 2155, faced with the undeniable reality of its immobility, the space agency reclassified the mission as a stationary research platform. While anchored in its final location, the rover continued its invaluable work, diligently taking measurements of the atmosphere and capturing several more images, including its last panorama from Troy, a poignant farewell to the Martian landscape. The rover was still able to perform crucial soil studies and extraction tests as the functionality of its robotic arm remained remarkably excellent. However, the rover needed to maintain a busy research schedule to efficiently utilize the power it was generating and to ensure the continued health of its onboard batteries. But the final Martian winter, a bitter and unforgiving season, was rapidly approaching. Over the subsequent months, the power generation from its dust-laden solar panels continually plummeted. By Martian Day 2196, it had once again fallen to the critical threshold of 150 watt-hours. Sometime on Martian Day 2208, it is widely believed that the rover suffered a decisive low-power fault. Its systems went quiet for good. Thus, it is demonstrably clear that for any Martian rover that relies primarily on solar power to function, the relentless onslaught of a dust storm, particularly one filled with slightly sticky, electrostatic dust particles, represents truly very bad news. If such a storm suddenly passes overhead, the gradual yet inexorable deposition of dust from its churning embrace is often sufficient to effectively block the vital sunlight from reaching the rover's solar panels. This pervasive coating, this insidious veil of fine particulate matter, has, tragically, spelled the end of more than one pioneering mission launched from Earth. However, these problems, this fundamental vulnerability, magnify exponentially when one begins to scale such storms to larger and larger planetary dimensions. Mars does not possess a perfectly circular orbit around the Sun. Consequently, every year during the Martian southern hemisphere's spring and summer, the planet reaches its closest point to the Sun. During this period, the planet, as a whole, experiences its warmest temperatures. For reasons that are not yet fully understood, it is during this specific time of year that regional dust storms begin a perilous process of merging and coalescing into a colossal superstorm, a meteorological entity so vast it can encompass the size of an entire continent. It is, of course, conceivable that several distinct dust storms simply happen to be forming independently and by sheer proximity begin to merge. However, the remarkable regularity, the almost clockwork precision with which these continent-sized storms manifest yearly makes coincidence an insufficient and ultimately unsatisfactory explanation. Once the ambient temperature on Mars reaches a sufficiently warm threshold, these immense storms form with an almost uncanny predictability. Yet, these are merely the continent-sized ones. Scientists, as of yet, do not possess a comprehensive explanation for the even grander, more formidable stage above that, the truly planet-sized storms. These all-encompassing global dust storms occur on average once every 3 Martian years, a frequency that seems sufficiently short to rule out the influence of Milankovitch cycles as their primary origin. Milankovitch cycles, which are long-term variations in Earth's orbital parameters, typically operate on timescales spanning thousands to hundreds of thousands of years, making them an unlikely driver for a phenomenon that recurs every 5.5 Earth years. Perhaps there is some intricate aspect to the Martian dust cycle, a subtle yet crucial requirement for a period of restocking that necessitates these 3 Martian years, or approximately 5.5 Earth years, to fully replenish and prepare for the next colossal atmospheric upheaval. As of now, the precise mechanisms and the underlying triggers for these truly global events remain tantalizingly shrouded in mystery. While most dust storms on Mars typically endure for only a few days, these apex storms, these planet-spanning behemoths, can persist for weeks or even for months. The profound impact of these extended and all-encompassing storms on any human technology, or indeed any human presence around the planet, would be truly immense. Scientists possess a valuable tool for measuring the availability of sunlight on Mars known as aerosol optical depth, or AOD. This metric quantifies is being absorbed or reflected by the pervasive pollutants, or, in the case of Mars, the ubiquitous dust, suspended in the air. For context, on Mars, the AOD is typically around 0.5, indicating a relatively clear, though still dusty atmosphere. For rovers such as the Diligent Opportunity, or landers, like the Sensitive Insight, an AOD of less than 2 is generally required for their onboard batteries to effectively charge and sustain their operations. To provide a terrestrial comparison, the thick, choking smoke caused by a massive wildfire here on Earth that begins to turn day into night would register an AOD of approximately 7. These planet-sized Martian dust storms, however, push the AOD to staggering values ranging from 9 to an astonishing 11. Such extreme figures represent a near total blockage of incoming sunlight, effectively plunging the entire planet into a prolonged and profound twilight. In 2018, a storm of this unprecedented magnitude proved to be the ultimate undoing of the resilient Opportunity rover. Swamped by the pervasive dust, which effectively rendered its solar panels useless, the rover was forced into an involuntary hibernation mode. Without any power flowing through its onboard heaters, the wildly oscillating and extreme day-night temperatures of the Martian environment inevitably caused something critical within the rover's delicate systems to break. It never woke up from its enforced slumber, a poignant end to a truly remarkable mission. These colossal storms pose a significant problem even for rovers equipped with onboard nuclear batteries like the ever-vigilant Curiosity. While such rovers are not dependent on solar power, the sheer density of the dust clouds is often thick enough to severely impede or even completely block radio communication to and from the surface. This means that scientists on Earth have little choice but to patiently and anxiously wait out the storm's duration, effectively losing contact with their valuable robotic emissaries. But the impact of these storms extends even further, affecting not only surface assets, but also the delicate satellites orbiting high above. The colossal amounts of warming dust suspended in the atmosphere cause the entire Martian atmosphere to expand. This expansion pushes some of the tenuous atmospheric gases into the orbital paths of satellites. Consequently, these orbiters are forced to burn their precious and finite fuel reserves, executing critical course corrections to ensure that the increased atmospheric drag does not cause them to gradually lose altitude and eventually come crashing down out of the Martian sky. Every maneuver, every expenditure of fuel shortens their operational lifespan, making these storms a costly and enduring nuisance. If, as future human settlers, one were hoping to establish a permanent presence on Mars, one would undoubtedly need to devise ingenious ways to overcome these formidable issues. Solar-powered settlements would simply not survive such prolonged and intense dust storms without a robust and independent alternative source of power. Furthermore, humans themselves do not fare well in such intensely freezing temperatures, making the loss of heating an existential threat. The potential loss of the ability to contact our orbiting satellites for weeks on end could also leave a nascent colony dangerously isolated and profoundly vulnerable. During those protracted periods of communication blackout, the human inhabitants would need to possess a considerable degree of self-sufficiency. If anything were to go wrong, if an emergency were to arise while a storm was raging, there would be simply no means to call for external help, placing an immense burden on the colonists' ingenuity and resilience. Still, in time, even these colossal, planet-spanning storms proved to be their own undoing. By blocking so much light from reaching the surface, the ground eventually ceases to be warmed sufficiently to create the powerful upwelling winds that initially lift and sustain the dust in the air. Without a continuous supply of more rising dust, these immense storms effectively starve themselves, gradually losing their impetus and eventually pittering out, leaving behind a slowly clearing sky and a planet once again bathed in the gentle, if dim, light of its distant sun. Do you ever wonder what the wind on Mars truly sounds like? You no longer have to merely imagine it. In 2018, the InSight lander, a marvel of engineering, successfully recorded the actual sound of Mars's wind utilizing its onboard seismometer. This sensitive instrument, which had not yet been deployed to the ground to detect subtle Marsquake vibrations, proved surprisingly adept at picking up the atmospheric murmurs. This is what it sounds like, although to truly appreciate the low frequencies and the subtle nuances, you will likely need either a robust subwoofer or a high-quality pair of headphones. This recording has not been sped up. These are, quite literally, the raw vibrations caused by the Martian wind as it swept across the solar panels of the lander, its frequency converted into audible sound waves. What is truly fascinating is that we are not merely relegated to imagining the wind passing by in sight. The lander was also able to capture remarkable footage of ethereal water ice clouds gracefully drifting overhead, visibly showcasing the direction of the wind's invisible currents. Yes, despite its current reputation as a barren and desiccated wasteland, there still exists a tiny yet persistent amount of water vapor suspended within the thin Martian atmosphere, occasionally coalescing into these wispy, crystalline formations. While the overall Martian atmosphere and its accompanying weather patterns remain profoundly inhospitable, these fleeting glimpses of clouds and wind offer a subtle yet poignant reminder of the planet's dynamic and often beautiful complexities. But what of Mars's soil? Many of us have undoubtedly seen or read the popular science fiction narrative, The Martian, a compelling story, in my opinion, about the ingenuity and resilience required for survival on the Martian surface. A central and memorable part of that narrative focused on the protagonist's audacious attempt to grow potatoes utilizing Martian soil. This raises a crucial and intensely practical question: how feasible is such an endeavor in reality? Does Martian soil truly possess the necessary nutrients for plants to grow? And, perhaps even more importantly, would there be any adverse or toxic side effects from consuming produce grown on an alien world? As it turns out, Martian soil does in fact contain a significant number of the essential nutrients that plants require for their growth. However, much like Earth, with its diverse range of soil compositions, some areas boasting nutrient-rich soil, while others are significantly nutrient-poor. The specific suitability of Martian soil for agriculture depends, critically, on where exactly one is located on the planet. Some regions would undoubtedly be far better suited for cultivating plants than others. However, it is vital to understand that the soil on Mars is not truly soil in the familiar terrestrial sense. It is more accurately described as regolith, a layer of loose, unconsolidated rock and dust. Crucially, it lacks the rich, complex history of organic matter, decomposition, and biological activity that defines Earth's soil. It has not been, for billions of years, intimately mixed and enriched by the tireless work of worms, insects, and the decaying remnants of countless plants. This fundamental absence of organic content is a significant distinction. In a remarkable experiment conducted in 2016, researchers here on Earth successfully grew a variety of crops, including tomatoes, rye, radish, peas, leeks, spinach, garden rocket, cress, quinoa, and chives, in an imitation Martian soil. The results were surprisingly encouraging, with the simulated Martian soil producing only slightly less produce than would have been achieved in Earth's natural soil. Interestingly, the same experiment was also conducted with imitation moon soil, which, as expected, yielded approximately half the amount of produce. Yet, even in this less hospitable medium, these resilient crops still managed to grow, with only spinach truly struggling to perform adequately. It is important, however, to include a crucial caveat. Regarding these promising results, organic matter was deliberately added to the simulated Martian soil in this experiment. Specifically, cut-up grass was incorporated to serve as a natural fertilizer, enriching the soil and, crucially, to fluff it up, improving its texture and allowing water to more easily pass through to the plant roots. Without this vital organic amendment, the plants would not have lasted long, a stark reminder of the terrestrial difference. Another significant barrier that scientists would need to overcome when attempting Martian agriculture is the abundance of heavy metals and, importantly, a compound known as calcium perchlorate present in the Martian soil. Calcium perchlorate is a type of salt which, like heavy metals, is toxic if consumed in sufficiently large quantities. This perchlorate and these heavy metals present in the soil would inevitably be absorbed into the growing plants, posing a direct threat not only to the plants themselves, but also to any humans who subsequently consumed the produce. The toxic elements would accumulate within the human system, presenting a serious health hazard. However, perchlorate is not entirely without its potential benefits in the context of Martian survival. In fact, in a curious paradox, it could actually assist future human colonists. For one thing, perchlorate possesses the remarkable property of drawing or sucking water directly out of the thin Martian air. This extracted atmospheric water could then be collected and utilized as a vital source of liquid water, an absolutely critical resource for sustaining life on the arid red planet. Furthermore, perchlorate, under certain conditions, can also release oxygen, another absolutely critical checkbox for human survival on Mars, providing a potential in situ source of breathable gas. In summary, then, it appears there are two major problems that must be ingeniously overcome when considering the prospect of growing plants on Mars. The first is the fundamental need for effective fertilizer. Revisiting the narrative of The Martian, the protagonist, Mark Watney, cleverly overcame this particular problem by utilizing processed feces from the habitat's toilet as a potent fertilizer. Typically, the use of raw feces in agriculture is dangerous due to the presence of various pathogens. However, if the feces are meticulously processed and treated to effectively kill these harmful pathogens, they can then be safely and effectively employed as fertilizer. Once agricultural production is successfully underway within a Martian colony, one could, of course, always rely on the rich compost collected from old spent plants and food waste, creating a sustainable, closed-loop system. The second significant problem is the presence of those toxic chlorates. Fortunately, this challenge appears to have a simpler and more elegant solution than one might initially imagine. By simply running water through the Martian soil, these soluble perchlorates would be effectively rinsed out and leached away. The water, now containing the dissolved perchlorates, could then be collected, and the water and perchlorates subsequently separated through a purification process, ensuring that nothing is wasted. An intriguing alternative also being explored is the use of specialized perchlorate-eating bacteria, which, as a beneficial byproduct, release oxygen into the environment, offering a dual advantage for future Martian agriculture. There is a profound and multifaceted reason why the ability to grow plants is so critically important in any future human colonization efforts on Mars. Beyond the obvious benefit of providing a sustainable food source, which in itself renders the colony significantly more self-sufficient. There is also compelling evidence suggesting that fresh foods, such as vibrant tomatoes, nutrient-rich blueberries, and crisp red lettuce, are excellent sources of vital antioxidants. Having a consistent supply of such fresh and nutritious food items readily available in the challenging environment of space and on an alien planet could have a profoundly positive impact on the psychological well-being and mood of the colonists. Furthermore, these antioxidant-rich foods could also provide a degree of valuable protection against the insidious effects of radiation in space, an ever-present threat to human health beyond Earth's protective embrace. So, in essence, it is indeed possible to cultivate plants in Martian soil, provided that the crucial aspect of fertilization can be effectively managed and that the issue of toxic chlorates is adequately addressed. Adapting to Mars's unique and often challenging environments is, quite simply, the name of the game when it comes to the monumental undertaking of colonization. Space agencies around the world are diligently utilizing and developing a wide array of different technologies meticulously tailored to adapt to the highly specific environments found on Mars. One such example of ingenious adaptation is the deployment of aerial vehicles. The atmosphere on Mars, as we have explored, is remarkably thin, a mere fraction of Earth's dense, breathable air. For a long time, the very notion of sustained flight within such a tenuous atmospheric envelope was widely considered to be an impossibility. Yet, through groundbreaking engineering and a profound understanding of aerospace principles, this perceived barrier has been overcome. The pioneering spirit of the Ingenuity helicopter stands as a testament to this remarkable achievement. Ingenuity, a marvel of lightweight materials and two sets of precisely engineered carbon fiber blades, was able to achieve a truly groundbreaking total of 72 powered flights over the course of its 3-year lifespan on Mars. It traveled an impressive distance exceeding 17 kilometers, capturing, along the way, some truly spectacular images of the Martian surface. This mission stands as a prime example of how engineers meticulously adjust and refine their technological designs to specifically suit the unforgiving and often counterintuitive conditions of an alien environment. Beyond the realm of helicopters, other fascinating designs are also under active development. One particularly cool concept involves exploration robots that possess the ability to walk rather than solely rely on wheels. If one has been following the progression of robotic explorers dispatched to Mars over the years, a fairly consistent design becomes readily apparent. The Spirit, Opportunity, Curiosity, and Perseverance rovers, and even the Jurong rover, deployed by another nation, all share a similar six-wheeled configuration, with large, often robust bodies, some exceeding 2 meters in height, meticulously equipped with a diverse array of scientific instruments and high-resolution cameras. This consistent design is a direct consequence of the principle that form follows function. Wheels are an inherently efficient and relatively straightforward means for a robot to traverse relatively flat and open terrain. Furthermore, a large body provides the necessary volume and structural integrity to accommodate a substantial amount of scientific equipment and power sources. However, as with all engineering choices, wheels also come with inherent downsides, limitations that restrict the kinds of places these valuable robots can effectively explore. Recall the unfortunate setback suffered by the Spirit rover in 2009, when it became deeply stuck in soft sand, a treacherous trap from which it never escaped. Although scientists initially harbored the hope of continuing to utilize it as a stationary research platform for studying the immediate area, its immobility effectively marked the end of its primary mission. This was particularly true when its desperate and prolonged efforts to extricate itself ultimately drained its precious batteries, leading to its eventual demise. A similar, though fortunately less permanent, incident occurred with the Opportunity rover in 2005. In its case, Opportunity, after being stuck in spinning wheels for just over a month, was, fortunately, able to escape and resume its mission. However, there was also a pivotal moment in the first year of Opportunity's mission when it was meticulously exploring the Endurance crater. The exposed rock layers etched into the sides of this impressive crater were deemed ideal for answering crucial questions about the ancient history of water on Mars. Yet, Opportunity possessed inherent limitations regarding the maximum steepness of a surface it could safely drive on, typically around 30 degrees. There was significant uncertainty whether it would be able to successfully extricate itself from the crater once it had driven into its depths. Ultimately, after careful deliberation, scientists made the courageous decision to send Opportunity into the crater anyway, recognizing that the potential scientific value to be garnered was simply too promising to forego. As it happened, Opportunity, defying initial anxieties, was able to successfully drive out and continued its remarkable exploration of Mars's surface for another 15 years. But all that invaluable science, all those profound discoveries, would not have been possible if Opportunity's wheeled design had meant it was irrevocably trapped within the confines of Endurance crater. Now, contrast that wheeled mobility with the capabilities of a truly remarkable and dynamically different robotic design. Consider this robot, known as Big Dog, developed by the cutting-edge robotics company Boston Dynamics, a firm renowned for creating some truly impressive and often awe-inspiring robots. One need only witness their Parker-performing humanoid robot, Atlas, a machine capable of running, jumping, and climbing over obstacles with an agility and fluid motion that is almost eerily human-like, to grasp the sheer sophistication of their engineering. In situations where the terrain is complex and uneven, one can immediately discern the profound advantages that legs can offer. Big Dog, for instance, could effortlessly traverse powdery soil conditions, even ascending challenging slopes, thereby expanding the range of areas it could effectively explore in an environment as rugged as Mars. However, it was a later, more refined version of their quadrupedal robots that truly captured the attention of space agencies. Meet Spot. Spot is a walking robot, originally conceived and designed for a diverse array of tasks here on Earth, such as the meticulous collection of data and the comprehensive mapping of industrial spaces, or for venturing into dangerous and inaccessible areas that are too hazardous for human entry, such as zones that are heavily irradiated. This versatile machine is capable of carrying weights of up to 14 kilograms and can execute repetitive tasks with remarkable precision. Crucially, it possesses the ability to walk up stairs and to confidently navigate over gravel and other uneven and challenging surfaces. It comes equipped with an array of cameras providing a full 360-degree view of its surroundings, allowing it to meticulously map the space it inhabits. Should it accidentally fall over, it possesses the remarkable ability to self-right itself, even from a completely upside-down position, a testament to its robust design and intelligent control systems. Unlike the wheeled rovers currently on Mars, which typically achieve top speeds of approximately 0.2 kilometers per hour, Spot can travel at a significantly faster pace, reaching around 5.8 kilometers per hour. But perhaps the most ingenious aspect of Spot's design is its intelligent and highly autonomous artificial intelligence. By continuously processing the information it gathers through its various cameras, Spot is able to construct a detailed three-dimensional image of its environment within its onboard computer. It then utilizes this sophisticated spatial understanding to meticulously determine the optimal path for traversing obstacles and navigating the terrain. One doesn't necessarily directly control Spot in the traditional sense with a joystick or intricate commands. Instead, you simply communicate your desired destination and the robot autonomously figures out the best way to get there, actively avoiding obstacles if they present themselves in its chosen path. If it begins to fall, it can intelligently assess the situation and rapidly calculate the necessary leg movements to arrest its fall and regain stability in a way that is almost eerily lifelike and impressively agile. It is precisely this blend of autonomy combined with Spot's incredible range of versatility and dynamic movement that renders it an ideal candidate for the challenging exploration of other planets. Direct, real-time control of a robot on another planet is simply not feasible. The immense distances involved between Earth and Mars result in significant and unavoidable time delays or latency for radio transmissions. There would be several-minute lags between a scientist on Earth sending a command and the robot on Mars actually executing that action. This means that a considerable amount of decision-making needs to be performed autonomously by the robot itself on location without immediate human input. This principle is already true for the rovers that space agencies have sent to Mars, such as Spirit and Opportunity. However, Spot, with its advanced AI, can elevate this autonomy to an entirely new level, pushing the boundaries of robotic exploration. Thanks to a collaborative effort with a prominent space agency's Jet Propulsion Laboratory, Spot is proving itself capable of working in concert with a series of other robots to explore Martian analog caves here on Earth. These robotic teams are meticulously exploring the entire layout of these complex cave systems, completely independent of human intervention. They are autonomously choosing their own paths, confidently walking over challenging obstacles, and demonstrating their ability to handle pitch black lighting conditions, dense smoke, pervasive dust, and even the presence of water. They possess the intelligence to recognize and identify points of scientific interest, and to then independently investigate them, relaying valuable information back to their human overseers at a later, more convenient time. One particularly compelling area on both Mars and our own moon that space agencies are eager to explore in future missions are caves. Caves are scientifically interesting for a multitude of reasons, offering unique and invaluable insights into the geology and potential habitability of these celestial bodies. Firstly, they provide scientists with a rare opportunity to peer deep into the geological strata of a planet without the formidable challenge and logistical complexity of needing to perform any extensive drilling. Drilling into an alien surface is an incredibly difficult and energy-intensive process. By exploring caves, scientists can gain direct visual access to the planet's internal structure, helping them to discern its composition and to determine whether liquid water was ever present within its subterranean realms. Secondly, caves represent inherently sheltered ecosystems. While features on the surface might be relentlessly eroded and altered over vast stretches of time by the ceaseless action of wind or the penetrating bombardment of cosmic radiation, caves offer a profound degree of shelter. This protective environment can act as a natural archive, preserving anything of scientific interest for us to discover, from delicate geological formations to potential biosignatures that might otherwise have long since vanished from the exposed surface. Indeed, some space agency programs are keenly interested in whether any microbial life, any extremophile bacteria, might have survived and perhaps even thrived in such sheltered environments on Mars, or at the very least, if their ancient remains might still be detectable within these protected subterranean refuges. Finally, and of paramount importance, this inherent shelter and the invaluable protection from the harsh and ever-present cosmic radiation also renders caves exceptionally promising locations for future human colonization. The natural shielding provided by the overlying rock would significantly mitigate the radiation exposure faced by human settlers, making these subterranean havens far more hospitable than surface habitats. This makes it all the more crucial for us to meticulously map out and thoroughly understand these cave systems in preparation for any future human missions. Currently, however, we face significant challenges in our efforts to explore caves on other planets. Taking photographs from orbiting spacecraft only provides limited information, typically revealing little more than the entryway or the immediate mouth of a cave. Scientists from orbit cannot effectively map the intricate and often labyrinthine internal structures of these subterranean formations. Wheeled rovers, like the venerable Opportunity, would undoubtedly struggle to explore such a cave system, as the ground within would likely be anything but flat. Passageways might become too narrow for a 2-meter-wide robot to effectively navigate, and the terrain would be inherently uncertain, filled with unforeseen obstacles. Perhaps worst of all, radio signals back to Earth would quickly become blocked by the thick, overlying rock, meaning that any robot requiring direct human input or real-time commands would not get very far into the cave's depths. In other words, a robotic explorer dispatched to investigate a cave on Mars would need to possess the remarkable ability to autonomously enter and thoroughly explore the entire subterranean labyrinth entirely on its own, with absolutely no prior knowledge of what the internal terrain might look like. It would need to be able to see and meticulously map the complex and often unpredictable terrain to autonomously decide how best to move around and over obstacles, and crucially to safely bring all that invaluable information back out to the surface for retrieval and analysis. And this, precisely, is what a prominent space agency's Jet Propulsion Laboratory, in collaboration with Boston Dynamics, is currently striving to achieve. By seamlessly combining Nebula, an advanced decision-making artificial intelligence, with the incredibly versatile platform of Spot, there is a profound hope that one day they will be able to dispatch several of these autonomous robots into a cave system on Mars or even on the Moon. The vision is for these robotic teams to independently enter and meticulously map these subterranean environments, organizing themselves and collaborating effectively as a group. Utilizing their onboard cameras, their dexterous robotic arms, and a suite of scientific equipment, they would identify and investigate objects of scientific interest, relaying that crucial information to each other, and then intelligently dispatching the robot carrying the most appropriate equipment to further study and photograph the object of interest. Currently, there is no set date, no definitive timeline for when Spot or similar robotic platforms would be deemed ready for the formidable task of exploring the Moon or Mars. This technology is still firmly in its testing and development phase. However, the tantalizing possibility that this advanced robotics offers is immense. One day, robotic dogs or similar agile, autonomous machines might form the very backbone of planetary exploration or even undertake crucial labor and construction tasks on Mars, laying the foundation for future human endeavors. Future human inhabitants on Mars would, by absolute necessity, need to be profoundly self-sufficient. It would be an immense and perilous undertaking, far removed from the comforting assurance of being able to call for immediate help from home, from our familiar Earth. Here, on Earth, we often take for granted the effortless ease of instantaneous communication. If you phone someone on the opposite side of our planet, you might experience, at most, a split-second time delay, a barely perceptible lag, in the transmission. At these relatively short, terrestrial distances, the speed of light, while still finite, is incredibly fast, rendering communication almost immediate. However, when we consider astronomical distances, particularly the vast expanse between Earth and Mars, the speed of light, while still immense, proves to be comparatively slow. On Mars itself, the sheer distance to Earth means that radio transmissions will be subject to a significant and unavoidable time delay ranging anywhere from approximately 3 to a considerable 22 minutes. This delay, it must be noted, is only one way. Accounting for the return transmission, the absolute minimum delay for a round-trip communication is a prohibitive 6 minutes. This makes a normal, real-time phone conversation or any interactive dialogue utterly impractical and indeed impossible. Text, audio, and video messages would, of course, be possible, but Martian settlers would have to be entirely prepared to fend for themselves and to make immediate, critical decisions without any direct or instantaneous guidance from Earth. This is particularly crucial in cases of emergencies or unexpected equipment failures, rendering remote operations or real-time assistance entirely unfeasible. The weight of responsibility for their own survival would rest squarely on their own shoulders. But let us assume, for a moment, that all these formidable difficulties, these myriad challenges, are meticulously overcome. Let us envision a future where the intrepid colonists successfully reach Mars and are ready to establish their enduring foothold. The crucial question, then, arises: where, precisely, would they settle? At the present moment, there is no single, universally favored, candidate location. However, several intriguing possibilities are under active consideration, each offering distinct advantages and presenting unique challenges. The planet's North Pole, for instance, represents a distinct possibility, primarily due to the undeniable presence of substantial reserves of water ice embedded within its permanent polar cap. Water, as we know, is an absolutely critical resource for human survival, and having it readily available in a concentrated form would significantly simplify the logistical challenges of a nascent colony. Another particularly interesting option is the immense 81-kilometer wide Korolev crater. This impressive impact basin is also, fortuitously, filled with water ice, representing another significant reservoir of this life-sustaining compound. While the Martian atmosphere is simply not thick enough to allow liquid water to pool on the surface for any extended period, pockets of water, securely locked up in ice, can be found at the bottom of craters, particularly where the temperatures remain sufficiently cold to prevent sublimation. There is also the profound possibility of settling near, or indeed directly upon, underground water deposits found in the vast subsurface permafrost beneath the Martian crust. Extensive studies, based on data meticulously gathered from a combination of Mars orbiters, have successfully revealed and comprehensively mapped out numerous locations for these hidden subterranean water reservoirs scattered all across the planet. While these underground ice deposits would undoubtedly be more challenging to extract than the more accessible surface ice, their discovery could potentially open the door to establishing colonies in more equatorial latitudes. These warmer regions, crucially, would be far more effective for energy production, utilizing solar panels as they receive a greater intensity and a more consistent supply of sunlight. Mission planners would likely seek to combine this promising finding with a location in the northern hemisphere where the ground elevation is considerably lower, meaning the atmosphere is comparatively thicker. This thicker atmosphere is perfect for slowing down and safely landing heavy spacecraft, providing an additional crucial advantage. As previously mentioned, another significant consideration when meticulously searching for a suitable settlement location is to ascertain if there are any lava tubes in the immediate vicinity. A lava tube is essentially a long subterranean cave that formed during ancient volcanic activity when molten magma flowed through it, and then subsequently emptied, leaving behind fairly uniform and often immense tunnels. We observe many examples of these fascinating geological formations here on Earth. On Mars, these lava tubes could even be large enough to comfortably house entire buildings within their protected and naturally shielded interiors. While numerous lava tubes and other cave systems have been identified on Mars, suitable candidates for colonization would also need to consider the elevation of the location and the prospects of readily accessible nearby water resources, creating a confluence of desirable factors. Once a meticulously chosen site has been definitively selected, the monumental task of preparing and making the area suitable for a human habitat can finally begin. Not everything that future colonists could possibly need would fit into a single, colossal spaceship on the initial journey to Mars. Consequently, several Forerunner missions, autonomous and meticulously planned, will have to take place preceding the human arrival. These robotic missions will be tasked with laying the fundamental foundations autonomously for what the human colonists will ultimately require. There have been numerous architectural competitions stimulating creative ingenuity to find the most optimal design for long-lasting and resilient Martian habitats. Although as of yet, no single model has been definitively declared as the ultimate and universally accepted solution, a wide variety of innovative proposals have emerged. These range from designs that envision creating habitats primarily using the abundant water ice found on Mars to more organic concepts such as habitats constructed with the intricate and efficient design structure of fungi. However, the overwhelming majority of these ingenious suggestions converge on a common and pragmatic approach utilizing the ubiquitous regolith, the loose, unconsolidated soil found all over the surface of Mars to construct the habitat, employing advanced 3D printing techniques through the tireless work of autonomous robots. Unfortunately, robots capable of such sophisticated and large-scale autonomous construction do not currently exist in a fully developed state. Consequently, they must first be meticulously designed, engineered, and rigorously tested before this ambitious idea can even transition from concept to a tangible possibility. But the fundamental concept is compelling. It requires excavating the raw regolith material from the Martian surface, which would then be processed and meticulously mixed with collected water ice to create a substance akin to concrete. This robust and radiation-shielding material would then be 3D printed, layer by meticulous layer, by the autonomous robots, gradually forming the structural shell of the habitat. Robotic assistance and sophisticated artificial intelligence will be absolutely invaluable in preparing and constructing the habitat long before the colonists' arrival. Attempting to undertake such a monumental construction task by human hand once they are there would be an utterly impossible undertaking, particularly given that astronauts are confined to their cumbersome suits and the sheer scale of hard and prolonged manual labor required. Once the 3D printed habitat is structurally complete, it must then be capable of supporting the immense weight of additional regolith. These habitats are designed to efficiently protect their future inhabitants from the relentless onslaught of cosmic radiation. Therefore, in the final phase of many of these architectural proposals, a crucial recommendation is to cover the entire habitat with a substantial layer of even more regolith simply by shoveling it on top. This is because Mars, as we've discussed, does not possess A global magnetic field, like Earth, meaning that radiation is an ever-present and significant problem on its exposed surface. The more material, the greater the thickness of protective regolith that can be placed between the sun's harsh radiation and the vulnerable human colonists, the better they will be protected from its insidious and damaging effects. Once the habitats are suitably prepared and deemed safe for human occupation, the colonists can finally begin their arrival. Even with the indispensable assistance of the autonomous robots, they will still have a considerable amount of crucial work to undertake. This includes connecting up the power systems, meticulously setting up all the necessary equipment, and generally getting the entire site fully operational and running smoothly. While this intensive work is ongoing, they would likely have to reside in temporary habitats, perhaps their own spaceship in which they arrived, or possibly inflatable habitats designed for initial deployment. In any case, these temporary living quarters would not be particularly spacious and would only provide the absolute basics for immediate survival.